So in this video, we're going to look at a three-phase system, and we're going to look at the line-to-line and the line-to-neutral voltages. So in this case, this is a Y. It's actually kind of a upside-down Y here, but it's a Y to Y connection. So we have our generator is connected in a Y, which gives us this neutral point or this central point where the three coils are connected, and also our load. So this over here is our load that we're supplying, and it's also connected in a Y. Okay, and so when you look at this, you could really look at just one circuit at a time. You can kind of look and say, okay, I've got current is flowing out of here over, and then it's just going to return, because remember, it always takes the path of least resistance, so it's going to return back through the path of least resistance there, which would just be back through the neutral line. So but if we wanted to apply Kirchoff's voltage law, remember KVL, Kirchoff's voltage law, applies to any electrical circuit. And so if we started here at neutral and we went up through the first coil to point A, and we go down through the resistance here, and then down through this resistance to point lowercase b back to this point, right? And so that would be a complete loop. And so we could write the voltage, and so the voltage, the question then becomes, what is the voltage VAB? So looking at the circuit here, we have a voltage VAN, okay, VAN, which is a line voltage, okay, and that voltage is 10 volts at an angle of 0 degrees. VAB, or excuse me, VBN is also a line voltage, and it is at 10 volts at an angle of minus 120 degrees, right? Because they're always line, and you know, a wide, it doesn't matter whether it's Y to Y or delta. When you're looking at just these phases, they're always 120 degrees apart. Okay? And so so that's going to be minus 120 degrees. So the question then with KVL, what we're looking at is, you know, if you start at point B and you go to the neutral and then you go to point A, you're looking at you're looking at those voltage there. We can add those together, or if you want to look at it the other way, if you say we're going to go from point A and we're going to go around and through the circuit over here to point B, okay, so that's defined as VAB. VAB is defined as a line to line voltage. All right, and so we're going, as we go up through here, right, this is a positive and this is a negative, so we're going up VA, and then as we come around here and we come back and we're at B and we go back to neutral, okay, we're going into the plus and coming out the negative. So VAB is defined as being VA minus VB. Okay, so that's the definition of the line-to-line. VAB is VA minus VB. You could do the similar thing with V BC, right? VBC would be VB minus VC, and then VCA would be VC minus VA. And, so you can do that for all of those. Now, remember, these are phasors, right? We're talking about voltages that have both a magnitude and a phase angle. So if we draw the phasors, right, VA is going out this way, which is 10 volts at an angle of 0 degrees, and then, all right, so that's 10 volts, write that up here, 10 volts at an angle of 0 degrees, and VB is 10 volts, but we're subtracting VB here, so we're subtracting VB, which is 120, or I'm sorry, 10 volts. The voltage, the magnitude is 10 volts, but it's minus 120 degrees. Okay, so we're going to subtract that. Okay, so we're starting here, and we have the voltage is 10 at an angle of minus 120 degrees. So this is the angle minus 120 degrees. I'm sorry, that's not the angle minus 120 degrees. Minus 120 degrees would be over in this direction. So it's minus, the angle here would be minus 120 degrees. So it's 10 at an angle of minus 120 degrees, but we're subtracting it. So if we're subtracting it, then you're going to flip it 180 degrees, so it's actually going up this way. All right, so you know, when you add the negative sign, a negative is 180 degree phase shift. All right, and so the voltage is 10 angle minus 120. It's going down this way, but now we subtract that, so it's actually going up this way. So it's going up this way 10 volts, okay, at an angle of, if this is 120 degrees, then that would be 60 degrees. Okay, and so now if we are measuring, now remember this this was VA, and this one over here is minus VB. Okay, and I did not draw this to scale, but so VAB is now going this way. Okay, so VAB, the line-to-line voltage, is going this way. So it's, the voltage is ahead, all right, and it turns out it's going to be 30 degrees ahead. If I would have drawn this to scale, I could actually use a protractor and measure the angle, and we would see that it's the angle is 30 degrees. And the magnitude, it turns out that the magnitude, VAB, so VAB now, is going to be VA the magnitude of VA, which is 10 volts, times the square root of 3. All right, so it's actually times the square root of 3, and I'll get into where that comes from in a second, at an angle of plus 30 degrees. All right, and so if VA was 10, so this would be 10 times the square root of 3, at an angle of plus 30 degrees. All right. And so let's look at a triangle. All right. If you look at a right triangle with a 30-degree, we're looking at a right triangle here now, so this would be perpendicular. Okay. So this is a right triangle with a 30-degree angle. Okay. Well, it turns out that when you look at this, all right, so with a 30-degree angle, the adjacent side, let's just say that the magnitude of the adjacent was like, say, 1/2, then this side over here would be this, actually the adjacent would be the square root of, okay, square root of 3 over 2, and this side would be 1/2. And so basically what we're saying here is, now that we've got this, we've got VAB is going here. So if we were to drop this, and make a right angle out of it, okay, so if we made a right angle out of this, it's bigger than VA by the square root of 3. It's not writing too well, but so if we drop this right angle here, this kind of green section that I drew here is another. It's basically the square root of 3 times VA, this entire length. Okay, so VA was 10, but the magnitude of VAB is the square root of 3 times that value. Okay, so that's where this square root of 3 comes from. It comes from the sides of a right triangle with a 30-degree phase angle. And so what you see in three-phase systems, when you look at the voltage and you want to calculate the voltage, okay, so VAB is the line-to-line voltage, okay, so it's like the line-to-line voltage, and it's equal to the square root of 3 times the magnitude of the line from A to neutral. Okay, the line is A to neutral, and plus 30 degrees. Okay. And then VBC is going to be 120 degrees behind that. Right, so that would be the square root of 3, okay, times VAN, and it's 120 degrees behind this, right? So you've got plus 30 minus 120, right, which would be minus 90. Okay, so this is actually going to be minus 90 degrees for VAN. And then VCA, right, is going to be the 30 plus 120, which would be 150 degrees. All right, so there's a 30-degree phase shift between the line to line and the line to neutral. Now notice though, the line to lines are 120 degrees apart, right? The line to lines are 120 degrees apart. The line to neutrals are 120 degrees apart. But when you say, okay, I'm going from a line to neutral to a line to line, there's going to be a 30-degree phase shift.